Hello, everyone. Um, so this is not an Advent of Code uh, problem-solving video. Some feedback that I got from my last video was that um, even though it was interesting from a problem-solving standpoint, or sort of showing how you would use APL to arrive at a solution, there's still some ground to cover with regard to just usage of the primitives and how you structure things and what some of these weird symbols mean. So I thought that I would put together a short crash course on APL and some of these primitives. I don't think we'll talk about all of them, but at least go over the most important ones. And the goal with this is to get you to a level of familiarity with the language where you can follow along with the rest of the videos. Now, so there's a lot of existing resources and documentation. If you go to dialogue sites, they have some great documentation. They have a full-length book called Mastering APL, which is really quite comprehensive. There's a channel on Stack Exchange called the APL Orchard, or the Apple Orchard, full of extremely helpful people. They'll answer any question that you have about the language. That's how I got started, in all honesty. And I'll link some of those resources, but just to tell you that this is this is not going to be a definitive tutorial by any means, and there are lots of existing resources out there if you want to dig a little bit deeper. So before we get started, let's talk about this website, tryapl.org. So if you, for whatever reason, don't feel like downloading the interpreter from Dialog, the interpreter is available for like Windows, Mac, and Linux, but if you don't feel like installing it or you just want to try some stuff quickly, this website is great. So you get, if you click on the Learn tab here, there's a bunch of different tutorials, closer look at some functions, reduce and scan, lots of like sort of release notes, all this sort of stuff. These articles are good. The primer will tell you, if you mouse over, it'll tell you, it sort of groups the primitives into these different categories. I think this is pretty useful. And if you mouse over, it'll give you examples of each one. And this APL keyboard over here is kind of interesting. So if you click it, you get this overlay. And basically the way that inputting these characters works is you use the backtick character on my US keyboard layout. This is the key to the left of the 1. It's shared with tilde. You press backtick and then any one of these letters to get the APL character pictured here. So like iota is a really common one. This is bound to the I key. So if I just do backtick I, then I get this iota character. And iota can be used to generate numbers from 1 to whatever you specify. And let me turn this keyboard layout off so that stops popping up. And then you can sum this. You can do all the stuff that I'm about to show you right here in the browser. It's pretty great, and I think there's even some additional links. Yeah, so like Mastering Dialog APL, I was talking about this. Fonts and keyboards. Well, about this reference card is awesome. Actually, I'm just going to take a look at this real quick. So I don't know. If you're serious about APL, I highly recommend printing this out and sort of having it handy, because this really does cover all the different use cases for all the different primitives. It looks a little bit intimidating maybe right now, just because there's so much information. But believe me when I tell you that once you start getting into it and really using the language, a lot of this stuff sort of flows naturally. It's very well designed. Thanks, Mr. Iverson. Yeah, so if you want to follow along with my video here, then you can use tryapl. But for the rest of this video, we will be using the interpreter here. This is the dialog calls it the remote IDE, or the RIDE. This is, as far as I know, the default client on Mac and Linux, I think. There's also a Windows only client that's a little more in depth and has more features. It has like a debugger, and you know, some other stuff. I don't use any of that advanced functionality, to be honest, and I think RIDE is a little more streamlined for my usage, so that's what I use. RIDE is actually an open source project, so you can go check it out on GitHub, see the installation instructions and everything there. Okay, cool. So let's see where to start. First of all, so when you start up your APL interpreter or you're using try-APL or whatever, you are dumped into this this REPL, read eval print loops. So this is just like Haskell or Python or any of these languages. So one of the first things that you can do is you can just use it like a calculator. So you can do like 1 + 2. That's cool. You know, you can do 6 divided by, and again, you know, when I'm using these symbols, you can mouse over any of these on the top, so you can see that I input the divide sign by backtick equals. Dialog does, so when you use the client, it does ship with a keyboard layout that allows you to input these characters by like control press. However, I enjoy the simplicity of just having one keyboard layout, so I tend to use backtick for everything. Slightly less efficient, but it works just fine for me. So you can do like 6 divided by 3, blah blah blah. You know, you can take the previous result, you can multiply it by 2. You know, whatever. This more or less works like you expect. The important thing about APL is that it is strictly right to left, which means that these functions here, whether arithmetic or not, don't have any precedence associated with them. Well, it's not strictly speaking true, but for our purposes right now it is. So, you know, in a normal language, let's say maybe you want to do like 6 + 3 divided by 4 - 1, right? So this is 9 divided by 3. So in APL, because it's evaluated right to left, you actually don't need the parentheses here, because 4 - 1 is going to be evaluated first, and then it will be fed to the division function. You do keep the parentheses here because it's on the left. And so, you know, if you keep this in mind, it can save you some extra parentheses, and you know, it's just generally in APL we're like building up these functions or these lines that are evaluated right to left. And you can kind of think of it like a pipeline or something like that. We're just successfully sort of applying these functions to the different data that we get out. And yeah, let's see what else. Oh, so even when we're talking about arithmetic functions, basically in APL, all functions can take either 1 or 2 arguments. So these are known by the monadic forms and the dyadic forms, which sounds complex, but basically when you're using one of these functions in its monadic form, you're just giving it 1 argument. And when you're using it in its dyadic form, you're giving it 2 arguments. This comes from the Greek, I think. And it's important to note that when I say monadic, it doesn't have any sort of relation to Haskell or any of these other languages that sort of have some category theory influence. This just literally all it means is that the function takes 1 argument or 2 arguments, right? So for instance, minus. Minus by itself is a negate function, right? So if you do -5, you'll get -5. And so in APL, negative numbers have this sort of high minus sign to distinguish from the actual minus function, right? So if we do minus -5, then we'll get 5 back. However, so this is minus in its monadic form. It's basically negate. However, of course, we can also use it in its dyadic form, where you give it arguments on both sides, and you get something like this. And so because it's strictly evaluated right to left, there's no ambiguity in parsing. So if you see something like this, it might look a little bit weird, but basically you just you have a function here. It has one argument on its right and it has another function on its left. So because there's no data to operate on its left, then the parser knows that we're using the monadic form here. So this will be -2, and then it'll be 6 minus -2, and we should get 8, and we do. Yeah, and that monadic dyadic pattern sort of applies to all of these. We'll go over the most important ones, but you can basically see when you look at this, it appears like this in try APL2 if you're following along in the browser. But basically, yeah, each one of these little documentation snippets will tell you what the monadic function is and what the dyadic function is. And again, all that this means is just one argument or two arguments. Okay, cool. So we have your basic arithmetic functions. We have plus, minus, times, divide. Monadic divide is reciprocal, which is kind of nice. Probably end up using that in one of these problems at some point. And then monadic times is direction. So this is jumping ahead a little bit, but if we apply this to a list like this, it just basically tells us whether it's less than 0, equal to 0, or greater than 0. You get stuff like this. Natural log, yeah, this is basically, so this character here is for logarithms, matrix inverse, matrix divide. I've honestly never used this one. Pi times, yeah, this is basically, this is how you get a bunch of trigonometric functions. These are rarely used in advent of code. Factorial and binomial. Factorial is sort of self-explanatory. 6 factorial is 720. And again, like you write it like that instead of this because we're evaluating right to left, right? So we're taking 6, we're feeding it to factorial. In other programming languages, you might do this, but you'll get a syntax error here. And then binomial, I think this is read like, oh, sorry. So if we do like something like this, this is 6, choose 2. Yeah, there's 15 different ways to do that. Question mark, this is for random numbers. So we can, well, I'll talk about lists in a second. So we can generate, a random number from 1 to 10, like so. Yeah. Okay, cool. Yeah, I guess now is a good time to talk about arrays. So as you may or may not know, APL is sort of famous for being an array-based language, which means that we really only have one data structure, and that's the array. But we have excellent support for that single data structure. So we can do things like, let's say that we have a list of 3, 4, 5, right? There's our list. We can add 7 to this list, right? And we get what we expect. So we're sort of taking 7, we're adding it to each element of the list. We can also do something like this. We can add the list 1, 2, 3 to the list 3, 4, 5, and we get this. But once you start adding together lists, in general, the length has to agree. So here, this will fail because this 4 is just hanging out here and it doesn't have anything to add over here. If you just have a singleton or like a scalar value, that's kind of an exception. The interpreter knows to kind of scale that out to all the other elements of the list without getting technical about rank and this other stuff. And this, of course, applies to our other arguments. So now we can do something like this. We can times, yeah, so like this. Cool, so that's arithmetic. Obviously, we want more out of APL than just being a calculator. That's where some of these other functions come in. Yeah, so like absolute value, residue, this is all kind of fine. Minimum, maximum. I used this one in the day 1 solution to do a floor or a round down. So that's useful to know. We'll skip these for now. Yeah, these are your Boolean logic. So bools are represented in APL by either a 0 or a 1. Nothing else, so there's no truthy, falsy values. So, you can say 1 equals 1. That is true if you try and tell it like 2 equals 1. Oh. Okay, forget what I just said. Equals is a bad example. Let's say that we said, so like 1 or 1, right? Or 3 or 1. Oh, huh. Yeah, no, that's true. Greatest common divisor. Okay, forget everything that I just said. I think you'll get a domain error on some of these if you try and apply them to a list of zeros and ones. But yeah, okay, cool. So these are all your sort of Boolean arguments. So you can do like 3, 5, 6 equals 4, 5, 9. You'll get a list of 0, 1, 0. This is sort of a piecewise comparison. You can, just like with plus, you can sort of expand this out. So you can do like 9 equals, whatever. And then, yeah, you have less than or equal to, greater than, not equal, which is kind of nice to have a single character for this. Right. And then, so notice how equal here, when you compare two lists, it's sort of doing a piecewise comparison. If you want to compare the whole list, you can do this match operator, which is 3 lines. And this will tell you if the lists themselves are equivalent. So those two were obviously not, but if we do like 1, 2, 3, match 1, 2, 3, then we'll get, this. Tally will tell you the length of a list is useful, right? So that's 3 elements long. This is 5 elements long, whatever. Yeah, and then we have OR, and these kind of have some logical NAND, NOR. These, at least for OR and AND, these kind of have these additional function of doing greatest common divisor or lowest common multiple. So they do apply on numbers outside of the 0, 1 domain. Logical NAND, I think, does not. So if I do like 1 NAND 2, yeah, it'll give me a domain error. But yeah, so this is like, if you have 0, 1, 1, 0, 1, and 1, 1, 0, this would be the result of ANDing these two Boolean arrays together. Yeah, and then, we have a lot of other operators here. Let's go through a couple more, and then we have a lot of other functions here. We can go through a few more, and then I can talk about operators, which is where things really start to get interesting. Yeah, so up arrow, mix, huh? Should I talk about? No, that's fine. So we'll just talk about the dyadic case of this right now. So you can do like 3 take, 1, 2, 3, 4, 5, 6, 7. 1, 2, 3. I'm going to jump over and talk about iota because I'm tired of typing these out. So iota in the monadic case will generate a range of numbers, from 1 to whatever number you specify there. So for example, if I wanted to only take the first 5 elements of this list, then I can do so. So we have this sort of inverse, which is drop. So if we drop the first 5 elements, we get this. And you'll see me, so I think in the previous video I did like a 1 drop. This just basically gets rid of the first element. These will also take negative numbers. So for example, if -1 take means take the last element. That works like so, and this works for drop as well. Yeah, what else? Should we talk about nested lists? Yeah, sure, why not? So, this work? Sorry, let me turn boxing on. I like to have boxing on because it will tell you when it gives you this nice sort of box when you're dealing with nested lists. A nested list just means you can think of it as like a list of lists. So it's like a list of pointers to more lists. If you take a look at the length of this thing, it will tell you that the length is 2, whereas if you take the first element, it will tell you that the length is 3, because the first element of this list is actually the list 1, 2, 3. And I guess now would be a good time to explain that this right shoe in the monetic case means first. So you take the first element of the list. Let me jump ahead and talk about row. So row will tell you the overall shape of an array, and it also allows us, so like if let's say that I have a list of numbers from 1 through 9, and if I do row, then it will tell me that I have 9 elements in that list, right? The interesting case is this dyadic application of row, which allows you to do reshape. And you can reshape into arbitrary dimensions. So APL arrays are not just limited to 1 dimension or 2 dimensions like a matrix. You can have n dimensions, really. So like, for example, I can reshape the list of numbers from 1 through 9 into a 3 by 3 element matrix. And if I ask for the shape, and this is row in the monadic case, if I ask for the shape of this, it'll tell me that it's 3 by 3, which is correct. And by the way, everything that we're talking about sort of naturally extends to arbitrary dimensions. So, you know, I have this 3 by 3 matrix and I want to add 4 to it. That just works, right? Yeah. So, you know, you don't have to worry about loops, maintaining pointers to these individual elements or any of this. Like basically in APL, you can just work just as easily with matrices or like higher rank arrays as you can with you know, scalars or just one-dimensional lists. By the way, rank in APL is the word for the number of dimensions of an array. And if you are interested, you can find rank by taking the length of the shape, right? So this is a rank 2 array because it has 2 dimensions, each of length 3. Yeah, we can talk about some more of these. So like reverse, right? So if I have a list of numbers from 1 to 9, I can reverse it, right? Reverse also works with, again, arbitrary dimension arrays. This is going to be the case a lot of the time. So, you know, it basically reverses along this axis. If you want to reverse along the other axis, you can do, what's this one called? Rotate first. Yeah. Oh, reverse first. Yeah, sure. This basically flips it, you know, among its first axis. Right? Everyone with me so far? Hopefully. You also have transpose, which sort of, I mean, if you're familiar with NumPy or linear algebra or whatever, this is sort of basic stuff. And, you know, these are all available as single character functions. They all work like you would expect them to work. All right, let's start talking about operators, because this is where things get fun. And by the way, there's a lot of primitives that I'm skipping over. I haven't talked about how you sort things. I haven't talked about like index of, which is very important, or membership. You know, like I can tell you 1, 2, 3, 1 to 14, 15 is in the list of numbers from 1 to 9. 1 to 14, 5. And you can see that these two and this one is in the list of numbers from 1 to 9, as you would expect, and 14 is not. So this is very commonly used primitive. Anywho, okay, operators. What's a good example? I think maybe the best example is this guy here. So this is the commute operator. Basically what an operator does is it modifies the behavior of the function on its left, or sometimes it's right. Mostly it's left though. So like, subtraction is order dependent. I always get this mixed up on whether it's commutative or associative. Let's say it's commutative. So so 6 minus 3, produces 3, but 3 minus 6 produces a different result, -3. However, the commute operator will switch the order that the arguments are presented to this function. So if you're using commute on this minus sign here, this is going to be equivalent to 3 minus 6, right? And again, because APL is strictly evaluated from right to left, there's no parsing ambiguity, there's none of that. So yeah, you can just say that this modifies the minus function and switches its arguments around. Another fun operator is slash. So slash in the sort of used as an operator here will reduce. That's a good way to explain this. Okay, let's imagine. So let's say that I have like a number of, or the list of numbers from 1 through 9. What reduce will do, and let's say that we took, let's say that we were reducing with the plus function, addition. It will take this function and it will put it between each of the members in the list. So plus reduce is equivalent in like Python or Haskell to sum, right? So if we want the sum of the first 9 numbers, we get that. And that's what you would get if you did like 1 plus 2 plus 3 plus 4, etc. Okay, cool. What else can you do with reduce? Yeah, you can multiply. The sort of equivalent of this is expand. I think it's called expand. No, it's called scan. And that will basically store the intermediate results as it scans the array from left to right. So this is sort of the results of repeated addition applied to this list. So, coming from a normal imperative language, you would do pretty much all of this by writing loops, for loops, while loops, whatever. In APL, it's quite rare to write a loop. You kind of do loopless programming by combining these different operators. And I guess this is sort of equivalent to, if you do much functional programming, you're probably used to using like maps and folds and this kind of stuff. This is the same idea. Yeah. So let's cover, since I mentioned map, let's cover for each. I think it's called for each. Each, yeah. So if I wanted to add the element 3 to the list of numbers from 1 through 9, I can totally do that. An equivalent way, by the way, this is kind of contrived, don't actually do this in practice, is I can say for each element in the list of numbers from 1 through 9, add 3 to it. And this jot here, basically, you can think of this like function currying. Like basically I'm hard coding this function to take 3 as the left argument. And this will give you the same answer, right? You have to be careful with each because APL gets a lot of its power from operating on arrays that are as large as possible. It's able to use specialized vector instructions, and the primitives in general are like very finely tuned. Like Like they're really fast, but it only works if you're operating on arrays. And when you start using for each, now you're slowing things down. Like this has to be done in serial. Yeah, it's you have to be careful. So basically, if you see a way to use the array-based approach rather than using like for each, then you should do that. But it's just sort of an explanation. Let's see, what else? I should talk about anonymous functions. So you're going to see APLers write a lot of stuff in curly brackets like this, and they're going to use characters like alpha and omega, lowercase alpha and omega. And all that's happening here, I'm just defining an anonymous function. This is just like lambdas in, again, Python, Haskell, what have you. And alpha will refer to the left argument of the function. Okay. Omega refers to the right argument of the function. So I could write my own sort of contrived addition function like this. So I have 4 and I have 8. They're getting fed into this anonymous function. 4 is getting bound to alpha, and 8 is getting bound to omega. And then they're being added together, and you would get 12, as you expect. This allows you to do stuff like, so the canonical APL example is something like average. So average is like length, what is it? It's sum divided by length, right? So you can do sum divided by length. And we'll have to put this in parentheses because, again, APL is evaluated right to left, right? So we can, and then we can assign this. This is the assignment operator. I haven't even talked about how we create variables. But variables can hold data, or they can hold functions. So functions are sort of, well, I don't know, if not exactly first order, first class citizens, then they're at least like economy plus. So we have an average function here, and then you can average like some number, some list, and yeah, like the average of this list, as you might expect, would be 5. The average of the numbers from 1 to 30, 15.5. Right? So what's actually going on here? I'll just review this. So this operator, remember, it takes the length of the list, and we're doing divide. So you can read this as the sum of the list divided by the length of the list, which is the definition for average. So that's how you would use anonymous functions like this. This is everyone following along? Everyone good? And let's see. So the other interesting thing about these anonymous functions is that you can recurse inside of them. What's a good? Let's say that we wanted. Let's say that we wanted to count. We want to write a function where it takes a number and then it gives us a list of sort of all the numbers decrementing by 1 down to 0. So sort of like a reverse iota, I guess. Okay, so we can write a recursive function like so. So we'll say that if w is less than or equal to 0, then we will return 0. Otherwise, we will do w append. This comma, I haven't covered it, but it just, it's like in many other languages, it's how you build lists. It's just append. Recurse, this little down triangle, means that we are recursing on w minus 1, right? Actually, sorry, I've introduced a few new elements here, so let's go through them in order. In anonymous functions, you can put together this, this is called a guard. Basically what this says, and it's denominated by this colon here, what this says is, hey, evaluate the expression to the left of the colon. and it should evaluate to a Boolean value, so 1 or 0. And if it's a 1, then just return the value to the right of the colon and stop, right? If it's 0, then continue. This little rhombus here is just a new line separator. So this is how we can pack several statements on the same line. This is just like a semicolon in C, let's say. Great, and then so we're on this next line, and remember, we're evaluating right to left. So we're taking omega minus 1, and then we are recursing on that value. We'll get some results back from that recursion, and we're taking the original parameter that was applied to the function and concatenating it with the result. So like if I apply this to, well, let's say that we rev iota, let's assign this to rev iota, and we are going to do rev iota 10. And we get a list of numbers from 10 all the way down to 0. And this is, if you're familiar with how recursion works, basically, we hit our base case down here at the bottom, we return 0, we concatenate 1 with it, we concatenate 2 with it, we concatenate 3, etc., etc., etc. So you're going to see this come up a lot. Recursion is basically how we do, if none of the primitives do the looping that we want, meaning like you can't do like a fold or a map or a scan or whatever, you'll use recursion, right? And I actually use recursion in the day 1 solution that I posted in the solution megathread. It's not the one that I derived in the recording, but okay, so let's see. I mean, there is a lot more that I can cover here. The key operator is really useful for like getting counts of the elements of a list. Stencil is kind of fun. It's kind of sporadically useful. Yeah, row I covered. The power operator, this is something that I used in day 1. It's kind of tricky to explain. I'm not really going to get into it in detail here, but so this is an operator. It modifies the behavior of some functions. And there's some work examples here. You can kind of see, so there's one here that talks about the fixed point, which is sort of what I was using in the day 1 solution. Yeah, I talked about nested lists at least a little bit. Honestly, I think that if you picked up everything in this video, we covered a lot of ground. So there's monadic, there's dyadic functions. Each one of these, weird symbols has different functionality depending on whether it's invoked in a monadic or a dyadic mode. So there's sorting. This is important. You should learn this. Man, you should learn. This is what's so interesting about learning APL to me, which is basically, you start off with all these symbols and it's fairly intimidating, but just start off with the basics. Start off with the arithmetic operations, some Boolean operations, some basic operators, so like reduce, expand. What was the other operator that I was talking about? Reduce and expand will get you quite a ways. For each, this is a good one. Yeah, you probably want to know about this. And then learn this anonymous function syntax. This is going to be very useful. And just kind of, when you're solving a problem, just like scroll through the language bar and see if any of these will be helpful. These are, again, like if we look at the TryAPL, site, these are all categorized sort of based on what you want to do. So you want to do search and sort. Okay, this is how you sort things. This is how you search a list to see if something exists inside of it. This is how you get the index of something inside of a list, right? Selection and set operations. Here's your union. Dyadic function is union, or intersection, right? Without, right? So sort of the disjoint set between. This is all useful, but just start with the basics. Don't try and learn it all at once. And I think, with some degree of perseverance, and it should be fun, right? I mean, it's fun for me. You'll be able to solve problems in no time. So hopefully this was helpful. Again, like, this is not meant to be comprehensive, so feel free to go into any of the other resources that I mentioned. And if you would like me to go into any depth on any of these topics, then just let me know and I can try and cover it in a future video. But I'm hoping that this sort of sparks some curiosity in you and will put you on some sort of level ground for being able to understand the Advent of Code videos that I'm going to be posting. Day 2 starts in like 10 minutes, so I better get ready. Anyway, yeah, thanks for watching, and I will see you next time.